It's mysterious and wondrous. Welcome to the world of relativity. Momentum is one of the most important concepts in mechanics. This video will introduce the definition and properties of momentum in relativity. In Newtonian mechanics, momentum is a three-dimensional vector defined as mass multiplied by velocity. The components of momentum in the x, y, and z directions are the mass multiplied by the component of velocity in each respective direction. In Lagrangian mechanics, momentum is defined not by velocity, but by the Lagrangian. Momentum is the partial derivative of the Lagrangian with respect to the generalized velocity, known as generalized momentum, sometimes referred to as canonical momentum. Each generalized coordinate corresponds to a generalized velocity and a generalized momentum. Therefore, a system with n degrees of freedom has n generalized momenta. A free particle in space can be described using the coordinates in the x, y, and z directions. Hence, it possesses momentum in these directions, each being the partial derivative of the Lagrangian with respect to the corresponding directional velocity. In modern physics, when we discuss momentum without specific clarification, it usually refers to the momentum as defined in Lagrangian mechanics, not the momentum defined by mass times velocity. In relativity, the definition of momentum also follows that of Lagrangian mechanics. In physics prior to relativity, the momentum of a free particle in Lagrangian mechanics aligns with that in Newtonian mechanics. The Lagrangian of a free particle is equal to its kinetic energy, which is half the mass times the square of the velocity. From this, we can derive that the momentum defined in Lagrangian mechanics is the same as the mass times velocity in Newtonian mechanics. In relativity, the Lagrangian of a free particle is no longer half the mass times the square of the velocity, and therefore its momentum is no longer simply mass times velocity. Having understood the definition of momentum, next, let's explore momentum in relativity, or more precisely, the Lagrangian momentum in relativity. List the Lagrangian for a free particle in relativity. Momentum is the partial derivative of the Lagrangian with respect to the generalized velocity. From this, we can calculate the momentum in the x direction. Note that in this definition of momentum, the speed of light is defined as 1, and v is the ratio relative to the speed of light, a dimensionless quantity. Therefore, the unit of momentum in this formula is the same as mass. If we restore conventional speed units, some changes need to be made to the denominator in the formula. Here, the speed unit is the conventional meters per second, and the unit of momentum is the same as in Newtonian mechanics, kilograms meters per second. When the particle's velocity is much less than the speed of light, the denominator approaches 1, making the relativistic momentum consistent with the momentum in Newtonian mechanics. Returning to the unit system, where the speed of light is 1. Similarly, we can write out the momentum in the y and z directions. We have previously discussed force velocity and how to calculate force velocity from velocity. From the respective formulas for calculating momentum and force velocity, we can see their relationship. Momentum is the mass multiplied by the spatial components of force velocity. You might ask, since the spatial components of force velocity multiplied by mass constitute momentum, what then is the product of its time component and mass? That is, energy. And because mass is a constant, energy and the momenta in the three spatial directions together form a force vector. We will delve deeper into these fascinating aspects of special relativity in future videos. One crucial reason why momentum is important is because of the conservation of momentum. This means that in a closed system, the total momentum remains constant. Consider two particles with masses m1 and m2. They move in a certain direction in space with momenta p1 and p2 respectively. Conservation of momentum implies that the sum of the two momenta does not change over time, which means the derivative of p1 plus p2 with respect to time is 0. In Newtonian and Lagrangian mechanics, conservation of momentum is derived through different logical processes. Let's examine each. In Newtonian mechanics, momentum equals mass times velocity. The derivative of velocity with respect to time is acceleration. Mass times acceleration equals the force acting on an object. Assuming these two particles are only interacting with each other and are not influenced by external forces, according to Newton's third law, the action and reaction forces are equal in magnitude and opposite in direction. Therefore, their sum is zero. This is the logical basis for conservation of momentum in Newtonian mechanics, arising from the equality and opposition of action and reaction forces. However, this logic does not apply to explaining momentum conservation in Lagrangian mechanics, as the fundamental concepts of Lagrangian mechanics do not include forces. In Lagrangian mechanics, let's calculate the derivatives of P1 and P2 with respect to time separately. According to the definition of momentum, express momentum in terms of the Lagrangian and the corresponding generalized velocities. Using the Euler-Lagrange equation, the derivative of momentum with respect to time is actually the partial derivative of the Lagrangian with respect to the corresponding generalized coordinates. Express the Lagrangian as kinetic energy minus potential energy. Typically, kinetic energy depends only on the generalized velocities and not on the generalized coordinates, while potential energy depends on the generalized coordinates. Therefore, the partial derivative of the Lagrangian with respect to the generalized coordinates is the partial derivative of the potential energy with respect to those coordinates. In a system composed of two particles without external fields, the potential energy depends only on the distance between the particles. Thus, the partial derivatives of the potential energy with respect to the two coordinates are necessarily negative reciprocals of each other, meaning their sum is zero. This derivation is not completely rigorous, but it shows that momentum conservation in Lagrangian mechanics is determined by the roles and functions of the generalized coordinates in the Lagrangian. Additionally, in Lagrangian mechanics, the concept of force is not a fundamental concept, but is derived from momentum, defined as the derivative of momentum with respect to time. Under this definition, force does not necessarily equal mass times acceleration. However, because of momentum conservation, the sum of the action and reaction forces remains zero. In this video segment, we have only briefly introduced momentum conservation under Lagrangian mechanics. In reality, any conserved quantity is determined by the symmetries of the system. The symmetry of spatial translation dictates momentum conservation. The symmetry of spatial rotation dictates angular momentum conservation, and the symmetry of temporal displacement dictates energy conservation. If you are interested in the relationship between conservation and symmetry, you can further study Lagrangian mechanics, which is beyond the scope of this video series. If a particle is subjected to a constant force, its velocity will continue to increase and could surpass the speed of light. What confuses many people is the contradiction between this thought experiment and the principle that the speed of light cannot be exceeded. Why the speed of light cannot be exceeded? Is it because a constant force cannot be applied to the particle, or because its velocity will not continue to increase? In fact, neither is the case. A continuous force is possible, and the velocity does increase during this process. The key is that the increase in velocity is nonlinear. To fully understand this issue, we need to start with the relativistic momentum formula. A particle with mass m moving at velocity v, let's outline its relativistic momentum formula. Display the relationship between velocity and momentum in a coordinate system. As the particle's momentum approaches infinity, its velocity approaches the speed of light. When a particle is subjected to a constant force, according to dp by dt equals force, it follows that the momentum changes at a constant rate. In this process, the momentum tends towards infinity, and the corresponding velocity approaches the speed of light, but can never reach or exceed it. This is the explanation for why the speed of light cannot be surpassed based on the relativistic momentum formula. Regarding the momentum formula, there's an issue concerning photons, which travel at the speed of light and have zero mass. In the momentum formula, both the numerator and denominator are zero. Do photons have momentum? We will discuss this question in detail in future videos, but before then, we need to first understand energy in the context of relativity.